When it comes to physics, there are some ideas that they feel a little weird, right? And the direction of acceleration, that's definitely one of them. Our gut feeling about which way things should be accelerating often clashes with how they actually move. But what if I told you there's one simple, single rule that cuts through all that confusion? Well, let's find it.
Okay, let's start with a classic. Picture this. You toss a ball straight up into the air. It goes up, it slows down, it kind of hangs there for a split second at the very top, and then it falls back down. So here's the question. Right at that highest point, at that instant where it's not moving up or down, which way is it accelerating? Is it up, down, or maybe not at all? Think about it, because your first instinct might just be a classic physics trap. See, the reason that question is so tricky is because of what I call the common motion trap. Our brains are basically hardwired to think that if something is moving in one direction, it must be accelerating in that same direction. And hey, sometimes that's true, but it's a dangerously incomplete picture.
So let's build this up from something we all get. Imagine a car. It's just cruising along, moving to the right. Dead simple. Its velocity arrow points to the right.
Okay, now the driver floors it. The car is still moving to the right, of course, but now it's going faster and faster and faster. It's speeding up. At this point, your intuition is probably screaming, it's moving right and it's speeding up, so the acceleration has to be to the right. And you know what? In this one specific case, your intuition is spot on. But here's the catch. Relying only on that logic is like trying to navigate the entire planet with just a compass. It's useful, for sure, but it won't get you everywhere you need to go. So, it's time to swap out that sometimes right intuition with a single, incredibly powerful rule that works every single time. No exceptions. This is the net force rule, and honestly, it's the only thing you need to know to nail this concept.
First things first, what even is net force? Well, think of it as the grand total, the combined result of all the different pushes and pulls acting on an object at the same time. If something is being pushed right and pulled up, the net force is the result of both of those combined. We call it a vector sum because the directions of those forces are just as important as how strong they are.
And here it is. This is the golden rule, the key that unlocks this whole thing, straight from Newton's second law. The direction of an object's acceleration will always, and I mean always, without a single exception, point in the exact same direction as the net force that's acting on it. I'm going to say that one more time because it is that important. This is the only rule you need. It doesn't matter which way the object is moving right now. It doesn't matter if it's speeding up, slowing down, or whipping around a corner. If you can figure out the direction of the total or net force, you have found the direction of the acceleration. That's it. End of story. Okay, so we have this amazing rule, but how do we actually figure out the direction of the net force? It might sound a little complicated, but it's really just a simple visual puzzle. Let me show you. It's really just a simple 3-step process. First, you just identify and draw all the separate force arrows acting on your object. Then you line them up, placing the tail of one arrow at the tip of the one before it. And finally, you just draw a new arrow from the very start of the first one to the very end of the last one. That new arrow, that's your net force. All right, let's try it out with an example. Imagine a box, and there are 2 forces acting on it. We've got force A, which is a pretty strong push, 10 newtons to the right. And at the exact same time, we've got force B, a weaker push of 5 newtons going straight up. So, if we add these 2 force arrows tip to tail, we draw our right arrow first. Then, from the pointy end of that one, we draw our up arrow. The final net force is the shortcut, right? It's the diagonal line that connects the very beginning of our chain to the very end. It's pointing up and to the right. And there it is. This shows the rule perfectly. Because we calculated that the net force points diagonally up and to the right, the acceleration it has no choice. It must point in that exact same direction. The box will actually accelerate along that diagonal line, even though not a single force is pushing it that way. Pretty cool, right? Okay, so we've got the rule. Now let's take it and apply it to those tricky situations, the ones where our intuition usually gets it wrong. It's time to finally draw a clear line between the idea of motion and the idea of acceleration. And this right here is the critical difference. This is the heart of the whole motion trap. Velocity, that's just telling you where an object is going in this exact instant. But acceleration, that tells you the direction of the overall push or pull that's actively trying to change its motion.
They have two totally different jobs.
A planet orbiting a star is the perfect example of this. At any given moment, its motion, its velocity, is pointing straight ahead, along its curved orbital path. But the only real force acting on it is gravity, right? That's the net force, and it's pulling it straight inward toward the star. So the motion is forward, but the acceleration is completely sideways, constantly yanking the planet into that circular path.
And that brings us right back to our original question about the ball. At the very, very top of its flight, what's the only real force acting on it? If we ignore air resistance for a second, it's just gravity, a constant downward pull. That is the net force. So the acceleration is also pointing straight down, even at the very instant its upward motion stops. So why does all this matter? Why are we focusing so much on this one rule? Well, because it's the absolute foundation for understanding how everything in our universe moves, from a tiny speck of dust to a massive galaxy. It's about learning to see the invisible forces that are behind all motion. So let's lock this in. Quick recap. Number 1, acceleration follows the net force, not where the object is going. Number 2, net force is just the grand total of all the pushes and pulls. 3, this rule is universal. It works for everything, everywhere, all the time. And maybe most importantly, 4, when you're not sure, trust the rule, not just your gut feeling. And that's it. 1, when somebody asks you which way something is accelerating, you don't need a crazy flowchart or a bunch of equations. You just need to ask one question. Which way is the net force pointing? Whatever that answer is, that's the direction of the acceleration. It's really that powerful and that simple.
So I'll leave you with a final challenge. A car is moving forward, but the driver hits the brakes. It's slowing down. Now, its velocity is still pointing forward, but to slow it down, to change its motion, which way does the net force have to be pointing? You've got the rule now. Think it over.